Today we embark on our first of a couple of lectures of linear algebra review, essentially. Everything that we're going to talk about in the next couple of days you should have seen in some form or another. Mostly probably everyone here knows what a vector is. If not, go take a linear algebra class because we're not going to be talking about it here. But what we're going to try and do is we're trying to do a review, but in between the reviews, I'm going to intersperse it with things that are new and that you haven't seen, so it's not just all boring boilerplate. And we're going to go pretty fast, but we're going to keep coming back to optimization problems in the middle. So it should be some new stuff, some old stuff. So I'm just going to get started. So everyone here has seen a vector, and all of you have also seen the idea of what we call the 2 norm of a vector. So if I have some vector x, and I can define the norm of the vector, and in particular, I'm going to now write this subscript 2 and write this as the square root of the sum of the squares of the entries, right? So when I write a vector x, I assume that its entries are x1, x2, let's say all the way up to xn. So if I have an n-length vector, then I can write the 2 norm of this vector. This is also sometimes called the Euclidean norm, or the and it's called the Euclidean norm because in the Cartesian coordinates, this represents the distance of the point of the endpoint of that vector from the origin, right? It's the magnitude of that vector. But the 2 norm is not the only norm that exists. In fact, there are many, many, many different kinds of norms, and that is what we're going to start to explore in this class. So we in fact have many different norms. And in general, a function f going from some vector space x into R is called a norm if 1, okay? The norm of the vector x is always greater than or equal to 0 for every vector x belonging to script x. So you see how this big script x is the vector space. This little x with an arrow on top of it is the vector x. Okay? And the norm of this vector is equal to 0 only under exactly one circumstance. What is the circumstance under which the norm is allowed to be equal to 0? Well, if the vector itself is the 0 vector. You can never have a vector that is not the 0 vector have its norm be 0. Okay? That's kind of property number 1 of all kinds of norms. Property number 2 of all kinds of norms. This came up last time when we were trying to figure out why the projection is the orthogonal, right? Why that point where you drop the perpendicular is the closest point to a point not on the plane. And some people were talking about the triangle inequality. Well, the triangle inequality is a key property of norms. It must satisfy the triangle inequality. In particular, if I have a vector x plus a vector y, and I take the norm of this, what does the triangle inequality that you've learned for the 2 norm tell you? What should be the relationship between this and norm x plus norm y? It should be shorter, right? And this should be true for every x and y belonging to your vector space. Okay? And the third property of norms, if I have some scalar, okay, if I take some alpha that is a real number and I scale my vector by that alpha, what happens to the norm? If I take 2 times the vector, what should happen to the norm? Scale by 2. What if I take minus 2 times the vector? What should happen to the norm? Scale by absolute value of minus 2, right? So this is absolute value of alpha times the norm of x. This is for every alpha belonging to reals and for every x belonging to your vector space. Okay? So now notice here, when I was writing the Euclidean norm up there, I kind of made a point to write that subscript 2 after the norm, right? But here, I'm not writing anything here. And so I'm denoting it as a general norm. When you've seen norms in the past, often in the first linear algebra class, you only talk about the 2 norm. And so you don't really distinguish between drawing the subscript 2 or not. Like often you might have seen this kind of notation to mean the 2 norm. But in this class, because we're going to start talking about different kinds of norms, it's important to think about this as a general norm versus specifically if you want to talk about something in the context of the 2 norm, you want to use the subscript 2. Okay? Yes, question?
Does the magnitude of a vector always refer to the 2 norm?
The magnitude of the vector always refers to the 2 norm. Yes. Okay. We're good with this? Yes, question?
Are we going to prove all of them for different norms, or is it just okay to say in general?
So you will have some homework questions where you will look at these. These are just, in some sense, axioms at this point, because we're saying if a function satisfies these properties, then it is a norm, right? So if you have a question saying like, hey, check if this function is a norm, then you have to go in and check that each of these properties hold for each of those, for that function, okay? Yes?
So for the first one, the if, that's like if and only if.
In this case, this is an if and only if, essentially. So if a function satisfies all 3 of these properties, it is a norm. If a function is a norm, it better satisfy all of these properties.
I mean that like the norm is 0 if and only if x is 0.
Yes, that is true. If this is an if and only if statement, you can write it as if and only if. X is 0 if and only if the vector itself is 0. Okay? Good. So now let me give you an example of a norm that is not the 2 norm. The LP norm. And this is basically a generalization of the 2 norm, where I'm going to write, instead of writing 2 there, I'm going to write a P. Okay? And what I'm going to say is that now I take this xi to the P to N, and then I'm going to take the pth root of this whole thing. Okay? So if I substitute P equal to 2, I recover the familiar object, right? But this is now a generalization. Instead of thinking about just the square root and taking the sum of the squares, I can think about many different things. Okay? So P can take any real value in this. There are particularly 2 values that are going to be of extra interest to us. Well, of course, P equal to 2 is of interest to us. It's a particularly useful norm. But if I take P equal to 1, this is called the L1 norm. And it's a particularly valuable one that we use a lot in the context of optimization. In the second half of the class, we're going to come to talking about L1 regularization and the lasso problem. And we will see that using a regularizer that is of the L1 norm type will help us get particularly sparse solutions for our optimization problems. And we'll talk about why this can be valuable. Right now, we're just going to introduce this. But the L1 norm, so I write this 1. So what is the first 1 over 1 is just 1. So I don't really have to take any kind of square root here. And so this is just the sum of the absolute values of all of the entries. Okay? And the second interesting case is going to be P equal to infinity. This is called the L infinity norm. And what happens when you take 1 over infinity? 1 over infinity is kind of 0, right? So to understand this quantity, you actually have to understand it in the limiting context. And when you take the limit of this thing, what happens is that this is actually going to give you max over all entries I. So it's going to pull out that entry of the vector that has the largest absolute value. Why is that going to happen? Because basically, as you raise this to higher and higher powers, the largest entry is what is going to dominate. And that is what is going to be preserved. Okay? So these are two particular norms that are going to be of interest that we're going to talk about in this class quite a bit. So in the context of the 2 norm now, there's a very useful inequality. Yes, question?
LP norms only for integers?
No, you can have LP norms for non-integer values as well. Yes. The question was, are LP norms only for integers? Okay. So what is the inequality that is very useful in the context of 2 norms that you've all seen before in the linear algebra class? Anyone? Yeah, Cauchy-Schwarz, right? So what is the Cauchy-Schwarz inequality? It talks about the dot product of vectors in the context of the norms of the vectors, right? Anyone remember what the Cauchy-Schwarz inequality is? Just shout it out.
The norm of the inner product of 2 vectors is less than or equal to the norms of the inner product of the 2 norms.
Okay. So if I take x transpose y, and I want to compare this to norm x, 2 norm, norm y, 2 norm. What is the inequality between these? This is less than or equal to. Okay? And fundamentally, why is this true? What is this quantity here, x transpose y? Is there another notation that we can write this as? This is the dot product between these 2 vectors. This is also the inner product, right? Good idea to remember this notation. And what is the inner product equal to? If I have x transpose y, that's equal to x1 y1 plus x2 y2 plus x3 y3 plus xn yn, right? So it's the pairwise products of all of the entries, and then you sum them up. That's the dot product. And what does Cauchy-Schwarz tell you? Cauchy-Schwarz, the dot product, these are all related to something fundamentally geometric about the vectors. What is that geometric property that we're relating to? If I have 2 vectors, let's say x, and another vector y, and I draw these in my Cartesian coordinates, what can we say about these? When we're talking about dot product and we want to maximize the dot product, what do we know about when this dot product is maximized? Someone else? Yeah. Something happens when they're orthogonal to each other. That's definitely a special case. Good to keep in mind. So we want to think about the orthogonality. And if they're orthogonal, what does that mean about the angle between them? 90 degrees. Okay, so that's one case. What's another special case that we might want to think about? If they're parallel, okay. If they're parallel, in this case, if I'm drawing everything from the origin, what does 2 parallel vectors mean? They're linearly dependent, or the angle between them is 0, essentially, right? So if I think about a fixed x, I can rotate y in many different ways to have different angles between x and y, right? So let's think about this angle here. This angle here is theta. What can we write x transpose y equal to? Well, I know this is equal to norm x, norm y, times cosine of theta, right? This is basically the fundamental, it arises from the definition of the inner product. If you wanted to prove this inequality, or this equality, how could you prove this equality? Someone else. You've seen this before? How might you do it? Cosine 0 is one special case. How could you prove this in general? The cosine rule. Yes, you would use the cosine rule to prove it. Exactly. What kind of transformation would you need to do? You'd need to use polar coordinates. Right? The basic way to prove this is now to think about this x in terms of polar coordinates. So if I was to define this as some angle phi x, I'd define this as some angle phi y, and then I could write my vector x as equal to x1, x2 in Cartesian coordinates. Or what's another way in which I could write this? What's the other coordinate form that you've used other than Cartesian coordinates? Polar coordinates, right? And how do you write something in polar coordinates? You have an r and a theta, right? So in this case, what is the r? What is the radius? What is the distance of that vector from the origin? It's the magnitude, which is the 2 norm, right? So in polar coordinates, you would write x as r, which is now the 2 norm, comma, phi x, right? Right, is it r comma theta? Now you can use this to compute the Cartesian coordinates of x, the Cartesian coordinates of y, and this you can use to then verify this identity, for example, as one proof of this. Okay? You've seen this all before. If you don't remember how to do this, good idea to go back and review your notes on exactly why Cauchy-Schwarz is true, right? But once you have this formula for the dot product, once you have that x transpose y is this, can you see immediately from this why the Cauchy-Schwarz inequality is true? Why is it true? What's the one thing? Just shout it out, shout it out. Cosine is less than 1 always, right? The magnitude of cosine is less than 1. You take absolute values on both sides of this. Cosine can never be greater than 1. Therefore, the right-hand side magnitude must always dominate, right? Everyone with me? Give me some nods, thumbs up. Yeah, good, good. Okay. So this all helps us to basically be able to do projections, right? Also. Like when we're thinking about doing a projection of one vector onto another, what is the key quantity that we use? Again, it's the inner product. It's the dot product, right? If I want to project a vector x onto a vector y, what do I compute? Okay, one person in the class knows. What about the other? How many seats are there in this room? Everyone with me? Yes? No? You remember how to compute a projection? If you don't remember, you're going to go and look it up tonight. We did it yesterday, right? We talked about least squares, and least squares is essentially projections, right? You should have seen projections before. We're not going to be able to talk about projections in any detail, so I'm assuming that you know what a projection is. Okay? If you don't, I need you to go back and look it up, right? So in general, projection of a vector x onto a vector y should be x transpose y divided by norm y squared. Okay? This is just the magnitude of that projection. To get the vector, you would actually multiply by y. Okay, good. So I can see that you have some questions here, but I don't really have time to go into revising what a projection is. I'm assuming that you're going to all go look it up. Remember the proof of least squares that we did last class, right? That's essentially deriving what a projection is. What did we do? We derived the projection. We proved that the projection of a vector b onto the column space of A is given by A transpose A inverse A transpose B. Everyone remember what we did on Tuesday? Yes? Okay, good. So now, if I wanted to project x onto a vector y instead of a column space of a matrix, what special case of the matrix am I talking about? Y, instead of now being a whole matrix, what is the column space of just one column vector? It's just the span of that vector, right? So now, can you use exactly what we did on Tuesday to derive the projection of a vector onto another vector? Do you see how it's a special case of least squares? Yes? Nods? Okay, good. Homework. Go look this up. Figure it out. This is all great. You've all seen this before. This is all 2-norm stuff. We want to now move forward. Turns out that we can generalize Cauchy-Schwarz. Okay? Cauchy-Schwarz can be generalized to get a very cool inequality called Holder's inequality. Holder's inequality says the following. Let's say I have x and y that are 2 vectors in Rn, right? They're specific n-length, real valued vectors, okay? And let p and q be real numbers, and p and q be both greater than or equal to 1, okay? In that case, I can say something about x transpose y, but move beyond the 2 norm, and I can upper bound this not just by the product of the 2 norms, but also by the product of the p norm and the q norm. In the case that I have this special property, 1 over p plus 1 over q is equal to 1. Okay? So I choose a special q corresponding to a p, and now I can upper bound this in terms of any norms that I want, as long as, of course, they have satisfied this property. If I chose p equal to 2, what is the value of q that I would get? 2. So what do I recover as a special case? Cauchy-Schwarz, right? So everything connects up, everything is consistent. We don't have the tools yet to prove this inequality, so I'm just telling it to you. Once we have a little bit more information about convexity, we can actually go ahead and prove this. And so if we have time, we'll come around to proving this once we have a little bit more machinery under our belt, but we don't quite have it just yet. Okay? So that's it for what I wanted to talk about Holder's inequality. Now I want to introduce you to another concept. How am I doing on time? Okay, I'll pause. Questions so far? Yes? Can the LP norm be a complex number? Let's think about it together, right? So to be a complex number, what needs to happen? To be a complex number, you need to have a square root of a negative number somewhere, right? Some kind of an imaginary number has to show up, or an even root. No, p is a real number. P is always a real number. We're not dealing with, very few things in this class are going to deal with complex numbers. You're not going to deal with complex norms. That doesn't make any sense. This is all defined for real things. Yes?
Can you reiterate why p equals infinity? Like that norm is the max of the grid?
Yes, y is p equal to infinity, the max of xi. So basically, when I have many numbers, if I have many numbers and I keep raising them to larger and larger powers, if I look at the infinitieth power of all of these numbers, the number that is going to dominate is going to be the largest one. And then I'm going to raise all of that to 0, essentially. But that's going to be like reducing everything to 1. And so basically, when you take limits, you can use L'Hopital's rule to do this. When you take limits, you will find that the thing that remains is the max that comes out. So it's a limiting argument. Yes?
In Holder's inequality, what if p or q is infinite?
If P or Q is infinite, good, hold that thought, we'll come to it. What happens if P or Q is infinite? What if P is infinity? What is 1 over P? 0. So what should Q be?
1.
Okay, good thing to keep in mind. We'll come to that in a minute. Other questions? Yes?
So Professor, I want to ask you, like over there, you said x equals parenthesis, that 2 long and comma phi x. So every time you write that, do you mean we're going to do something like the above 2 rows?
No, I'm using the polar coordinate representation of x there.
Okay. That's the
Okay.
polar coordinate.
Yes.
Cool.
Yes? You can use polar coordinates to prove that x transpose y is equal to norm 2x norm 2y into cosine theta. Okay? Yes?
Will we ever care about a case where 1 over p plus 1 over q isn't equal to y?
Yeah, you might, but that's not, Holder's inequality doesn't hold. Okay. I'm going to move on. My chalk is running out. So now what I want to do is I want to go a little bit deeper into these P norms and Q norms. And I want to explore some of their geometric properties. And I want to talk about norm balls. Okay? So I want to define BP, which is the norm ball corresponding to the P norm, as the set of all x belonging to Rn such that the P norm is less than 1. Okay? So we're going to draw pictures for this, and because I cannot really draw anything beyond 2-dimensional, I mean, in theory I could draw 3-dimensional, but then you would all run out of the room because my degrees are definitely not in art. But so we're going to stick to 2 norm pictures. And sorry, we're going to stick to 2-dimensional pictures. So I'm going to think about really everything in R2, just so that I can draw pictures. And the first thing I want to think about is the 2 norm ball. Okay? So this you've seen. What does it mean for the 2 norm of a vector to be less than 1? How do you draw that picture? Make like hand gestures or something. It's the circle, right? The unit circle. Trigonometry, everything you've seen so far, for example, in trigonometry often says, consider something on the unit circle, right? Cosine, sine is all defined by vectors that are going round and round the unit circle, right? So this is the 2 norm ball. So this is the set of all vectors x such that the 2 norm is less than 1, right? Any point here, any vector here along this point has 2 norm exactly equal to 1. Anything inside must have 2 norm or magnitude exactly smaller than 1, right? Okay. So now, what about the 1 norm ball? So here, take a minute. I'm going to give you a minute. All of you draw the 1 norm ball in 2 dimensions. So let's do this together. So what does it mean for this 1 norm to be less than 1, right? Well, in the 2 dimensions, what can I write? I can write x1 plus x2 less than or equal to 1, right? This is what I want, absolute value of x1 plus absolute value of x2. And so if I'm drawing a picture of this, what are some points that I know are definitely going to be allowed? Like 1, 0, 0, 1. So, okay, so this is definitely there. This is definitely there. Any other points that are definitely there? Yeah. Okay. And so now absolute value changes what the function changes value depending on whether x1 is positive or negative, right? So in the first quadrant, this is the x1 axis, this is the x2 axis. x1 and x2 are both positive, right? So that means that this condition reduces to just being x1 plus x2 less than or equal to 1, right? Which is a linear constraint now. And can we easily draw the line that represents x1 plus x2 equal to 1? Right? And what is that line? We just drew 2 points on it, right? This is that line in the first quadrant. This is just x1 plus x2 equal to 1. Anything that's below it is less than or equal to 1. What about in the second quadrant? Now, x2 is still going to be positive, but x1 is going to be negative. So here what you want is you have minus x1 plus x2 equal to 1. That's the line you want to draw. Again, what is that line? We conveniently drew 2 points on it already, right? Both of these points are on this line. Does that make sense to everyone? Yeah, everyone with me? Are these the kind of pictures you all got together? Okay. And you get third quadrant and fourth quadrant. So what you get here is a nice diamond, right? And if you think about it, this diamond, are there points in common with the 2 norm ball? Right? How does this diamond kind of fits exactly into this 2 norm ball, right? Kind of a smaller, it's like a shrunken version of that. It sits inside the 2 norm ball. You increase the norm, the possibilities for your vectors have increased. You decrease the norm, the possibilities for your vectors have decreased. Do you see that relationship? Everyone with me? Any questions about this? Yes?
Is it true in general that if you increase the norm, like the unit ball,
Yes. Think about how you could prove that. What's the obvious next question I'm going to ask you to do? Okay. So what do you get for the infinity norm ball? What does this reduce to when you're in 2 dimensions? Max of norm x1 and norm, or in this case absolute value because they're just scalars. This should always be less than 1, right? So whichever is larger should always be less than 1, right? So these 4 points that we had last time, right? We had 4 points that were shared in common with the 2 norm ball. 1, 0, 0, 1, minus 1, 0, and 0, minus 1, right? These were all 4 shared in common. Are these all 4 points going to be here? Right? So we know these 4 points are going to be, again, play roles for us. So last time for the 1 norm, we kind of had this x1 plus x2 line. Is that a limit for us now? Is that a constraint? It's not, right? Can we have larger values? Yeah. What's the largest value we can have here for x1? And what's the largest we can have for x2? So we got 1, 1 is in scope, right? What about over here? Negative 1, 1. Here we have negative 1, negative 1, and we have 1, negative 1, right? So what we have now is this square, where this is 1, 1, this is negative 1, 1, and so on. And now when I think of this in the context of my 2 norm ball, what does this? This now is kind of on the outside of my 2 norm ball, and it's tangent to my 2 norm ball at all of these points. And so what you see is that you have the 1 norm, 2 norm, infinity norm, kind of the question that was asked before. As your norm increases, you're increasing the possibilities, right? You're never going to go beyond this square because you can't go higher than infinity. If you had a p less than 1, what you would have is you'd actually have curving slopes inside here that would show up like this. And you would have this like concaving diamond that would happen. That's what your norm balls would look like. Okay? So now that we have a sense of some of this geometry, I want to come to our first optimization problem of today's lecture. Okay? And I want to maximize over vectors x so I'm given some fixed vector y, and what I want to now do is I want to maximize the inner product of x with a particular vector y, subject to the x having a constraint on its p norm. Okay? Actually, let's remove this absolute value. It won't make a difference, but I think it's a little bit easier to think about it without the absolute value. We'll do it case by case, right? Doing it in general is always challenging. So first rule of math, life, engineering, anything, any class you ever take with me, for sure, when you see something complicated, what do? Find a simple case. Find an example, right? So we just learned about p norms. P norms are complicated. They have like pth roots and stuff like that. What is the case that we would like to start out with? What is the case you would like to start solving this for? 2 norm, right? So let's do this for the case p equal to 2. So we want to maximize x transpose y subject to 2 norm is less than 1. So what does that mean in this picture here, right? I have this 2 norm ball, and I have some y somewhere, right? Maybe this is my y. Maybe this is my y. Some candidate y's. What is the search space for my x's? What x's am I allowed to look at? Anything inside the unit ball, right? Okay. So now, from what you know, from what we've already studied, what x is going to maximize the inner product? Actually, okay, take a minute. Good. Take a minute, think about this. I want everyone to do this. Yeah, to repeat what was just said. So we know that x transpose y is basically equal to 2 norm of x, 2 norm of y times cosine of theta, right? So now if I have my vector x, right, this duster is my vector x, I know that it has to be of length 1 or less than length 1. I'm trying to maximize this thing, so of course I'm going to try to make the vector as long as I possibly can, which means I'm going to make it exactly length 1. And I can rotate it anywhere to be along this circle, right? So as I rotated it, let's say I was exactly orthogonal to y. If x was exactly orthogonal to y, what is the dot product between x and y? 0. Clearly a bad idea, right? If If I get closer and closer and closer to x, I keep decreasing the value of my theta, which means that my cosine theta keeps increasing, right? When I get exactly aligned to y, or I'm parallel to y, what's my cosine? 1. So, therefore, what is the x that I'm going to choose? I have x transpose y is equal to 2 norm x maximized if theta is equal to 0. And so if I want to maximize this quantity, I'm going to basically choose x that is exactly has angle 0 to y. But what other constraint do I have on x? It has to be in the unit ball, right? And y need not be in the unit ball. Y could be arbitrary. So how do I make a version of y that's in the unit ball? Normalize it, right? So I choose x is basically the vector y divided by the norm of y, right? This gives me a version that is exactly aligned to y, but is inside my constraint set. We're good? Everyone with me? Okay. This was the easy case. So now, what we want to do is think about, well, what if we have the 1 norm? Now we're inside the diamond. Okay? How can we go about tackling this problem in this case? Again, the idea is that, well, if you are stuck with a problem, start with an example, right? Try a y. Pick a particular y. See what happens. What might you choose? Okay? So maybe I'll give you a minute to do some experimentation before we come back together to work on this. Take a minute, talk to people, do an experiment. Okay, let's come together. So one way I like to think about this is just rewriting it a little. So I know that in this case, x transpose y is just x1, y1 plus x2, y2 plus xn, yn, right? And this constraint I can write as x1, absolute value of x1 plus absolute value of x2 plus absolute value of xn is less than or equal to 1. Okay? So I'm choosing to write this as kind of the, I'm not using the angle perspective here. I'm choosing to use this other perspective of x1, y1, x2, y2, xn, yn, because it's kind of more aligned to the constraint that I have. Okay? So this is one of the things that I want to try and teach you or help you see for yourselves in the course of this class, is that sometimes, like the fact that different functions have different representations, or the same thing can be written in different ways. For example, we saw in the Cauchy-Schwarz example or the inner product example, like there's times when it's valuable to write the inner product as x1, y1 plus x2, y2 plus xn, yn. There's times when it's useful to write it as, norm x times norm y times the cosine of the angle. And depending on the context you're in, trying out these different forms can actually maybe sometimes help you make progress. Okay? So different representations are a good tool to have in your back pocket when you're trying to do proofs and things like that. But here I'm trying to basically go for similarity. Like here I have something about the sums of the x's. So here's something also similar to the sums of the x's. Okay? The other thing I was thinking was like, well, what if I just tried a couple of things, right? So I know that I want all of this to be less than or equal to 1, the sum of all of these to be less than or equal to 1. So what might be a natural-ish choice if I was super, super lazy? And a lot of engineering is about how one can be lazy. What might be a guess that I would just try and play and understand and explore these functions? What are things that are easy to calculate? If I pick one of these folks to be 1, and what does that mean? The others have to be 0, right? It makes this really easy to evaluate, right? So if I pick, for example, if I pick x1 equal to 1, this implies that x2, x3, all the way up to xn, all these folks are 0, right? And then what is my x transpose y equal to in that case? All of these guys are 0, so it's just y1, right? Okay? So is that a good thing or is that a bad thing? It's a thing. I don't know if it's a good thing or it's a bad thing. It's a thing. But if y1 was minus 10, is it a good thing or a bad thing? Well, it depends on what the other y's are. But if I had y1 equal to minus 10 and y2 equal to plus 10, is it a good thing or a bad thing? It's a bad thing. What would I maybe have instead preferred to do? Make x2 equal to 1, right? Okay? Okay, so what might be a guess that you might want to make in terms of how to go about doing this? So you want to maximize this thing. And if you're going to do this thing where you're going to pick out 1, which one are you going to pick out?
The maximum of the y.
You want to pick out the maximum of the y's, right? Okay. So maximum in what sense? So if I have, let's say my y's are, I have y1, let's say my y is equal to minus 2, minus 100, and minus 3. Which y do I want to pick? So remember here we were just doing an example. Has anyone ever constrained us to pick x1 to be 1? We have this constraint. We just picked this refinement of this constraint. Open your minds. What else could we do here? Could we pick x1 equal to 2? No. But we could pick x1 equal to 0 and x2 equal to 1. But what else could we do? Is there any other way that we could use this constraint? What are other values that might be maximizing in some sense? -1, right? Okay? So now if this I paired with 0, -1, 0, what would I get as the inner product? Right? So what am I going to do now? So what does this suggest? Right? So I want to do I care about the maximum y or do I care about the y with the maximum absolute value, right? So how am I going to pick x in light of that? So I'm going to say choose xi equal to sine of yi for yi such that absolute value of yi is greater than or equal to absolute value of yj for every j. Right? So pick that y that has the largest absolute value, and then pick the x that has the sign of that, right? So if your largest y in absolute value is -100, then multiply it by -1. If your largest y is 100, then multiply it by plus 1, right? That makes sure that this constraint is always met, but allows you to maximize your dot product in the end. Does that make sense to everyone? Okay? So do you see how we've systematically thought through this in a sense? Okay. So does this mean, so what does this mean? So this says that, therefore, what is going to be, when I do this thing, what is going to be the maximum value that I get? Like, what is going to be the value of x transpose y? It's going to be the maximum of the absolute values of the yi's, right? This is equal to the max over I, because that's what we just argued. We're going to pick that x. But do we have a name for this? This is the infinity norm of y, right? Okay? But, wait. So, there was a question about Holder's inequality. What happens when p is infinity? You should be thinking about connecting these things up. But before we get to that, are we done here? We wanted to say, we're making a claim here. We're saying that, okay, this is a solution, right? This is one possible solution to this optimization problem. This is one possible allocation of x1, x2, xn. We want to find not just one, we want to find the best one. Have we proved that this is the best one? No, we just said that this is achievable, right? This is one attainable, achievable value. We want to see, is this the best we could ever do? And that requires rigorous proof, right? So we haven't given that part. So all we've done so far, thus, is achievable. When you find a solution that can achieve a value, that means that that value is achievable or attainable. This is like terminology that we will be using. Now we have to prove that it can't be beat. Our to-do is to show that you can do no better. Okay? And this is a common thing that you will often come across. It's a standard technique that is used in optimization problems, is that you show first that, okay, some value can be attained, and then you also show a bound on the problem, right? So you say that, oh, this max can be no bigger than 10,000. And then you show a strategy by which you can also attain 10,000. That means that that must be the max. So optimization, you think that it's all about solving things and giving a precise value. But actually, a lot of it is about proving bounds at these kinds of inequalities and going back and forth. And often optimization problems are solved by like kind of a closing in. Well, you must be smaller than this, you must be bigger than this, like you must be somewhere here. That's kind of a lot of how some of these problems, and particularly algorithms, will work. Okay? This is our first foray into this kind of thinking. So we got to do this thing, right? We haven't done it yet. So how are we going to show that we can do no better? Holder's inequality will do it, but we haven't proved Holder's inequality, so I don't like that particular solution. But Holder's inequality will do it, right? Holder's inequality gives us exactly that. Holder's inequality tells us that, look, if I choose p equal to infinity, or if I choose p equal to 1 and q equal to infinity in this particular case, x transpose y is always less than or equal to the infinity norm of y. So we can never do better than this by Holder's inequality. And therefore, once you can achieve that value, you're done, right? So Holder's inequality is definitely a valid proof, but we haven't proved Holder's inequality itself, so we're going to prove this from first principles. Okay, so how do we prove from first principles? Okay, so let's think about this quantity, x transpose y. And I know that this is basically equal to the sum x1, y1, or xi, yi, sorry. And now I want to be able to say that somehow I want to be able to say that this is less than or equal to, let me just call this y max for short, right, or the infinity norm of y. I want to somehow show this inequality between these things, okay? So I want to be able to pull out this y max part of it, okay? And what do I know? I know something about the sum of the absolute values, okay? So if I want to, I have this, and I want to be able to use what I know, is there any way I can upper bound this that makes this look more like the constraint that we have, more like the information that we have? Cauchy-Schwarz is definitely a thing, but there we're like invoking two norms. Here we're in the one norm world. Like, I'm just thinking about straight up pattern matching. There's absolute values up there. There's no absolute values down here, right? Can we use absolute values? Can we bring in absolute values somehow? If I was to, instead of writing this, if I was to write absolute values of everything, what would happen to the quantity?
Increase or equal.
It would only increase, right? Because the absolute value is always bigger than the quantity itself, right? So I can just write this as, this is upper bounded. By this thing, right? Okay? Which is equal, now, absolute value of xi, yi. Can I write this as absolute value of xi, absolute value of yi? Right? Absolute values you can bring them inside. It doesn't matter. Okay? Good. Now I'm kind of in business, right? Like I have absolute value of x1 plus absolute value of x2. I have some constraint on this. And now I have kind of the same thing, except it's always multiplied by these different yi's. What would be nicer than having a lot of different yi's multiplying every single x? What would be, like, if we had instead the same yi multiplying all of these x's? Could we then use the information we have about the sum of the absolute values? We could, right? Okay, so if I wanted to replace these yi's with some particular yi, which one would I choose? The maximum, right? So can I write this as further less than or equal to let's just say y max. Whichever y maximizes the absolute value. Okay? But now I can just, this no longer depends on I, right? So I can pull it outside the sum. So this is now y max times I going from 1 to n, absolute value of xi. But what is this upper bounded by? This is 1, so this whole thing had better be less than or equal to y max, which is equal to this thing, which is exactly what we wanted. Okay? Everyone with me here? Question?
Is this case like a more vigorous proof of what we did on Tuesday with like the jet fuel and the gasoline?
Not related to jet fuel and gasoline at all, in any way. That's just a formulation problem. Yes? Is this solution unique? What solution? Is the sign yi unique? Well, let's think about it. What if my vector y, the question is this optimization have a unique solution? What if my y was 100, 100, 100, 100, 100? Is the solution unique? Nope. Right? Yes, question?
I guess follow up to that. If y max is unique, what about the solution?
Then it's going to be unique, right? There's only one thing that you're going to pick. Okay? Good. So I want to do one last thing. Let me keep this up here. It was coming. You knew it was coming, right? So what happens in this case? Now you're searching over this square, right? Y is fixed. Now you want to say what x in the infinity norm ball maximizes my particular setup, my inner product, right? So how am I going to go about that? Take 1 minute to think about it. So now in this case, what does this constraint imply? What values, like if we follow the same pattern of let's do an experiment, let's play with this a little bit, right? What values of x are allowed here? Anything between +1 and -1, right? Basically, that make sure that your infinity norm is less than 1, because the largest. So as long as every single entry of x is between +1 and -1, you're good. Okay? So which one is easier to think about? An x that has like a 0.9 and a 0.6 and a point pi and like too many things, right? What is a vector that's easy to think about? 1, 1, 1, 1, 1, or -1, -1, -1, or just vectors of plus and minus ones are easier to think about, right? Okay, so our x transpose y is again equal to okay? And now if I just think about x1 and y1 being +1s and -1s, what is the maximum and minimum value of xi, yi? Given the constraint on my xi's. This is always going to be less than or equal to yi, or absolute value of yi, and greater than or equal to right? Because xi is always going to belong right? So this is less than or equal to what? Right? Okay. Is this an object you've seen before? Were you expecting this guy to show up anyway? What is this? Right? So you've now proved an upper bound. You've proved that in this case, you can never do better than the one norm of y, right? Is there a way that you could actually achieve this? What would you choose x to be? The sine of y, right? So you choose x. So how do you achieve it? The achievability is to choose xi equal to sine of yi. So you have a vector x, which is just plus and minus 1s. Whenever y is positive, you choose positive. When, plus 1. Whenever y is negative, you choose negative 1. And you're always going to get x transpose y equal to the sum of the absolute values of the y vector. Right? Everyone see this? Everyone with me? Yeah? So again, here's an example of how you've done this by showing a bound and then showing an achievability, right? In the other case, we did it the other way. First we showed the achievability, and then we showed the bound. Here we showed the bound first, and then we found an achievable solution. Question?
How did we come up with the bound here?
Which bound? This bound? Yeah. So xi, we know that the infinity norm of x is less than 1. Therefore, what is the largest possible value every value of x can take? It must be inside that box, right? We drew that picture. So what is the largest possible value of every entry? 1 or minus 1, right? It has to be, xi must be between this. Therefore, this must be bounded by this. Okay? Question in the back. I'll prioritize the back, sorry, since the back doesn't ask questions. Yes?
What if the bound is too high?
What if the bound is too high? So the bound might be too high, but we've proved that it can be achieved. We have this solution. So the bound, just because this is an upper bound doesn't mean you can achieve it. The only way we can say this is now equal to the 1 norm of y is both because we showed this, there's an upper bound, and we showed an achievability. Both parts are essential, okay? So that's it for today. See you next week. Homework due tomorrow, don't forget.